with the issues of CCS, carbon capture and storage, and we've been working in this area for about 12, 15 years. And it's sort of an area where you work a lot with technology, but you're forced to work with looking at commercializations. And the question which you have is actually, which you posed was actually, that would be a challenge which all of us working within CCS would love to have, where we're looking at these larger transportation systems. But some of the things which also comes in through our door is technologies which we didn't quite realize were there. And what I'm going to tell you about today is basically a technology which was around for a long time. It's called magnetohydrodynamics, and it's appropriate for power generation. And what it does, it basically increases the efficiency of existing power generation cycles. Right? So what I'm going to do is I'm going to talk a little bit about what happened in the past, and where we are at the present, and what this sort of offers for the future. And this forum here, and this arena, is the perfect arena to actually present this technology. And when Mike said, look, we're doing this with the big countries, do you have any technologies which are appropriate? We sort of said, yeah, I think this is it. Okay? So let me move on to the first slide, and presumably I'll go like that. Magnetohydrodynamics is about plasmas. Okay? Now, plasmas is basically the fourth state of matter. You can think of matter as being in solid, it's in liquids, it's in gases, but if you keep on heating it up, it actually goes into a plasma where the electrons kind of move away from the nuclei. So you've got free moving electrons wandering around. This about the majority of matter in the universe is actually in plasma form, but it's out in intergalactic space, and also the sun is a plasma. All right? So what magnetohydrodynamics really is about harnessing this type of energy. So the past history of MHD is essentially in the 50s, with Nixon going to Moscow. There had been the energy crisis, 1973, and MHD was suddenly on the negotiations and discussions. Okay, the US needed to be independent of oil from the Middle East, and they had a lot of coal, so MHD was the technology which they started looking at. So during the 70s and the 80s, there was major programs which involved both in the US and also the program in the Soviet Union continued and grew. And then MHD got caught up in international collaboration, which was great. In 1974, everybody started working together, because it was sort of like it didn't fit into the arms industry. There was a passive use of nuclear energy and MHD energy and things like that. So it had benefits. It's a win-win situation. Okay. By the end of the 1980s, beginning of the 1990s, it started petering out. The DOE had spent about $618 million on this. The Russians have probably spent something similar. All in all, we estimate it's probably about $3 billion worth of R&D had gone into MHD over a period of about 25 years. Okay. Now, so that sort of put a lid, a seal on what happened about 1992, 1993. It stayed there for about 20 years, basically. But the technology refocused a bit, started being looked at in hypersonics, a little bit of re-entry vehicles. NASA was working on MHD for plasma clusters, and there was also the issue of fusion power, tokamaks, and stuff like that. These were all related technologies, so it didn't really disappear on us. But nobody really looked at MHD for power generation until about 4 or 5 years ago, when we had some discussions with one of our clients called Shell. Okay, and they said, "Well, what about this? We have some IP on this, and we were wondering if we could start looking at this, because our role in this is basically we're at the forefront of seeing if something is commercial. We can try and identify. That's almost stalking horse for the majors. Okay, they'll throw out lots of these different technologies and see which one actually sticks, which one they can move forward to. Let me just tell you just one slide. This is the only technical slide we have, okay? And it's basically how is MHD different from the way which we do power generation today. And if you look on the top there, you will basically see that you've got a turbo generator which is rotating an electric coil inside a magnetic field. If you look on the bottom there, you will see that there's a jet engine or something, a combustor, which ejects a very hot plasma gas, which is then forced through an electric field. And if you put electrodes on either side of that, you can actually pick up direct electrical power. Now the good thing about it is if you do that before you actually do your conventional power generation cycles, like your steam cycle, things like that, you can have a topping cycle which can extract energy right at higher temperatures, and then you can still do your conventional power generation cycle. So MHD is seen as something which is compatible with existing technology that adds a topping cycle that increases the efficiency. Okay? The other aspect of it relates to that it's also compatible with carbon capture and storage. If you do this with oxy combustion, which is oxy-free, then you're also in a lot better position to clean out the carbon at the back end of the cycle. So it's sort of like you're going to be paying a little bit more expensive or higher, less fuel efficiency if you do the carbon capture. But if you develop this technology, you will regain some of the fuel efficiency. Okay? So it could be a net win-win situation. Here's examples of some of the technologies as it was in the past. These pictures were taken in the 1970s. This is the typical sort of channel which you push that hot gas plasma through. Two pictures there. The one on the right is showing a facility which is available, which was built outside Moscow. It's called the U-25. Right? It was a 25 megawatt power plant. So, if you look at what this sort of looks at, I apologize for those of you at the back, but this is sort of a picture of an overall coal-fired power plant, which is shown on the right there. And then the pictures, lines on the left there are sort of the MHD part, which is inserted in as the topping cycle. And if you look at the gentleman at the top there, he's actually inside one of these ducts, one of these channels. So you get an idea of the scale of this. And on either side of that channel, you can see some lighter portions. So those are the electrodes. Okay? For these channels, they were made of ceramics. Same type of technology which you find on the shuttle power systems. Yeah? So it's very advanced, hot technology, which was difficult to manage then, but it's more appropriate now because we have more technology, more knowledge around this. And so that's another reason why we can actually go and start thinking about doing MHD again. Okay? What can MHD do today? Okay, so it will increase the efficiency of existing power generation cycle. It applies to conventional coal gasification, nuclear power, and natural gas and oxy-combustion, which is for carbon capture technologies. It generates centralized power with zero emissions. Okay? It enables non-polluting use of low-quality coal. That's what we're thinking about. There are large programs in India, China, and Russia, as well as the US, which are looking at MHD for coal generation and for power generation. This is the technology which actually allows you to do this. Okay? It provides CO2 for enhanced flow recovery and storage. This is the other aspect of CCS, carbon capture and storage. The most sensible thing to do with CO2 is get it to make money for it. The way you do that is you put it into the oil fields, so you make incremental oil recovery. Okay? It makes good commercial sense. MHD allows you to do this. Okay? And it removes nearly all the major metals and hazardous waste and particles. Right? So, what was the problem then? There was a performance gap. And again, I won't spend too much time explaining that. But essentially what you see, those lines on the left of the graph there, they're showing what the MHD was doing at the time. The axis going up vertically is the amount of duration of testing which was done. Okay? The top of the axis is about a year, and the horizontal axis is the efficiency of the system. Now, in both cases, where you really want to be is you want to be in the top right corner of this graph. Okay? MHD was in the bottom left corner because it was challenging. Right? So that's the MHD performance gap. Now that's the gap which we started looking at, and we see we can actually start filling that. Right? This table, I'm not going to even start talking about because it's too much details, okay, but it's basically why is it doable today? And you'll see a list of things which were in the 1980s and the 1970s program, and we'll see how technology has changed today. Right? Now what this allows us to start looking at some very detailed technologies on ceramics, on inverters for power generation. A lot of it will come back to things which you were talking about, that GE was doing. I have to admit, we've been talking to one of your competitors, okay, about this, but this is something which nobody is going to do on their own, which is why it's the kind of perfect technology to also present to a forum like this. We've been working, the DOE did a lot of work on this, okay? The DOE is not going to pick up on this on its own, but it may actually be interested if we can say, look, there's a lot of vested interest in it. But the Russians have done by far the greatest amount of work on MHD. You probably still have the expertise there today. Okay? It would be wonderful just to be able to go over there, have a look around, and see what you got. Bring the people. We picked up a lot of the expertise, the old timers, real old timers in the US are still around. Okay? People are wanting to actually do this, and they believe it's doable now. Okay? I can see Mike's giving me 2 minutes. Okay? So anyway. We have what needs to be done in the near term, coordinate global expertise and identify the targets, determine status of ongoing MHD technology within key stakeholder nations, the BRICS. Japan had a major program, okay. European Union and the US fund near-term R&D that identifies available technologies and initiates necessary R&D. And they were talking about 3 to 5 year scales. Probably need to do about 3, 4 years, 5 years of fundamental refining itself. Okay, how do we go forward? And then you're looking at potentially getting in the medium term, 5 to 10 years, find a strategy for demonstration and commercial deployment. So they're talking about the commercialization roadmap. Okay, so we're talking about technology which has activity from today for about 10 years through to about 2025. That's when we start targeting this type of technology coming in. What would it do? It would raise the efficiency of your natural gas-fired power plants, Joule's combined cycle, was 60% now. MHD could probably raise it up to 65, maybe 70%. If you want to put carbon capture on those combined cycle power plants, it would reduce the efficiency to about 52%, while MHD would give you that extra 8%, which gets you back to where you are today with clean fuel. I think that's basically. I had one more picture. I might have to show this one. This picture is from the first joint meeting on MHD in Moscow in 1974. Okay, I can tell you that the Russian delegation is sitting along one side of the table, and the US delegation is sitting on the other. I spent a long time trying to work out who was sitting on which side of the table, looking at these gentlemen here. They're looking very serious, okay? But they did a lot of very good work together. And I think that's the kind of mentality which is trying to be fostered here as well. But this is something which we can actually collaborate on. And like I said, India and China have a major MHD program as well. And the Japanese are already interested in working on this. And we have a major player in the States who's interested in taking this industrially. I think I can say that we've also been working with EPRI on this as well. Okay? So there's interest starting to build up. Okay? Thank you very much.